On the noise. Okay, folks, we are continuing our discussion of Chapter 3, Section 1, which covers exponential functions and compound interest. We talked fairly deeply yesterday about the compound interest formula, and we're going to continue to work with it to start today. So again, the compound interest formula is A equals P times 1 plus R divided by N to the NT. We need to remember what all of these various letters stand for. A is going to be the final amount in the account. P is the principal balance, or how much you put into the account at the beginning. R is the interest rate as a decimal. N is the number of times you're compounding annually, which depends on whatever word is in the problem. In this case, the word annually tells us the N value. And T is the time in years. Okay? So we're going to go through these last two examples we didn't get to yesterday, and then we're going to finish up the section. So here we go. What does it take to become a millionaire? Well, let's say you won $10,000. Rather than go on a spending spree, you decide to invest the money in mutual funds that earn a 12% interest compounded annually. And then we have four different parts here. How much money will we have at the end of each of these time periods? So our principal balance, P, is 10,000. Our interest rate here is 12%, written as a decimal, which would be 0.12. And the word annually tells us that N equals 1, which is going to result in some relatively simple, by comparison, calculator work here, simpler than the examples that we did yesterday for each of these four parts. So if we want to know, well, how much money is going to be in that account after 30 months, we need to ask ourselves, okay, 30 months is how many years? Well, 30 months divided by the 12 months that are in 1 year would give us that T is 5/2 or 2.5. It wouldn't matter whether you use the fraction or the decimal in this case, because the decimal is not rounded, it is exact. Okay, so we take those values, we plug into our equation. So we'd say A equals 10,000 times 1 plus 0.12 divided by N, which is 1, to the 1 times 5/2 or 2.5 power. We're just going to feed that to our calculator. So we're going to type it in very carefully. 10,000, open parentheses, 1 plus 0.12. We don't need the divided by 1, because when we divide by 1, nothing happens. To the 2.5 or 5/2 power, because 1 times 2.5 is 2.5. And we're going to round this answer off to the nearest cent, which would be $13,275.32 would be in that account after just 30 months. Okay. On to the next part of the problem here, where time is 44 years. This time we just need to plug in 44. So again, A equals 10,000 times 1 plus 0.12 over N, which is 1, to the 1 times 44 power. And again, we're just feeding that into the calculator. So 10,000 times 1 plus 0.12 to the 44th power would be, again, we're going to round this off to the nearest cent, $1,464,175.04. So there you go. It'd take 44 years. So I probably will take less than 44 years. Let's see where we're at after 45 years. So T equals 45. Again, A equals 10,000 times 1 plus 0.12 divided by 1 to the 1 times 45 power. and we feed it to the calculator. $1,639,876.04. All right, I want everybody to try part D, get an answer. I'm going to give you about, I don't know, a minute. Shouldn't take more than a minute to plug that into the calculator. And let's see what we get. After 100 years, how much money would be in that account? I personally would want to know where they find this 12% interest, because I've never seen that at a bank. That's a pretty high interest rate. This was mutual funds, maybe. I've never invested in one of those. All right. So again, hopefully we're not stuck here. We've got time is 100, which means A equals 10,000 times 1 plus 0.12 over 1 to the 1 times 100 power. And we feed our calculator. Okay, I am seeing that that account would have a lot of money in it. $835,222,657.30 is what I am seeing in the account. Questions on this example while I grab it and move it into the other thing here. Got to get this out of the way, though. It's going to be a challenge, I think. I can attach it to the bottom. Come on. Find somewhere to put it where it's not in my way, which is going to be a challenge, I think. It's not really in the way there. There we go. Okay. And that is pretty well what I need. There we go. Clipboard. There we go. We'll just copy this over here. Add it to what we had from yesterday. And we'll resize it later. Any questions before we continue? Unmute now and ask if you've got them. Otherwise, we're going to move on to the next example. All right. Nobody's jumping at the opportunity, so here we go. Okay, after 25 years, an initial investment of $3,000 into an account earning interest that was compounded quarterly is worth $13,296.14. What was the interest rate? Okay, so this problem is different from the standpoint that we're solving for a different value. We're not solving for A, we're solving for R. So we go in here and we find all the other numbers. 3,000 is our initial investment. That's our principal. So P is 3,000. We've got the final value as well. A is 13,296.14. We have the time, which is 25 years. And the word quarterly tells us that N equals 4. Okay, so we go in and we find everything that we can. There are 5 variables in the compound interest formula. So as long as we have 4 of them, we should be capable as pre-calculus students of solving for the 5th. So we plug into our equation. Again, our compound interest formula equation is A, which is $13,296.14, equals P, which is 3,000, times 1 plus R, which we don't know, over N, which is 4, to the n times t power, which would be 4 times 25. So we can't simplify a lot here. The one thing we can simplify is 4 times 25 is 100. So we probably should go ahead and do that. $13,296.14 equals 3,000 times 1 plus r over 4 to the 100th power. So now we're essentially solving an equation, just like we do in algebra. It's no big deal. The first thing we need to do is divide both sides by 3,000, which would get rid of the 3,000. So we divide both sides by 3,000. So we do $13,296.14 divided by 3,000. Now notice that decimal, that's a repeating decimal. So we need to keep as many digits as possible for our intermediate work. Do not, repeat, do not round off the number from the calculator. Keep every single digit that you've got. Okay, if you round in the middle, you're going to screw up your answer. Do not round until you get to your final answer. Now, anybody can unmute, anybody can say it in the chat. How do we get rid of the 100th power? How do we undo exponents?
Square root 100 or something?
We do take a root. Wouldn't be a square root. It would be a root, but yes. So this is tricky in the calculator in theory. So let me write this out here. We are going to take the 100th root of each side. Okay. So we're going to take the 100th root of the decimal on our calculator. And on the other side, well, that'll take care of itself, because in reality, what's going to happen is the root and the exponent are going to cancel each other out. So on your calculator, to take the 100th root, you type in 100, then you hit the math button, and you choose option 5, xth root. So again, you type in the 100, then hit the math button, and select option 5, the xth root. Then you need to type in the decimal, 4.432046667. Again, we do not want to round that decimal off. That is 1.015000002. And I know it seems silly to keep that 0.000002, but it might make a difference in the final answer. So we need to keep every decimal our calculator provides us with. On the other side, all that happens is the root cancels the exponent. We'll pause there for a second, make sure everybody's ready to move on. Again, to take that root in your calculator, you type in 100, which is the index, then hit the math button, then choose option 5, the xth root, which will insert the 100 in the index spot for the 100th root. Okay? Now, what is our next step here to solve for r? What do we do next?
Take the LCM.
Nope. We could, but we don't need to. That would just be another step where we let's just, how do we isolate that fraction? What do we need to do to get r over 4 by itself?
Multiply by 4.
Oh, we could do that, but we don't need to. That's what I just said. Okay, we could do it. It would be okay, probably. Yeah, let's just subtract the 1. Okay, let's just subtract 1 from each side, which would give us 0.015000002 equals r over 4. Then we'll multiply by 4. Okay, so now we'll go times 4 to cancel out the decimals, or the fraction, sorry, cancel out the denominator. So 4 times Our decimal would be 0.06000008. Now we are going to round that off. Interest rate usually is rounded to 4 decimal places as a percentage. So we would look at the 5th digit, tells us to round down. So in reality, this is going to be 0.06 or a 6% interest rate. Okay, we could solve for any, repeat, any of the values in this problem. Any of the values in that equation we could solve for. You have the algebra skills to do it. You just have to use your brain. Okay? One of the things that has been added to your Delta Math assignment is some problems where you have to solve for things other than A in the compound interest formula. Okay? So just keep that in mind. As we move forward. Okay? All right. I'm actually making one more minor adjustment to it right now because I just thought to myself, you know, we can make this better. Okay. There we go. Now we're good. All right. Any questions here on example 2 before we move on to the natural number, which is what we needed to know to actually do what we had the other day that Mr. Wells probably should have mentioned or noticed on Delta Math. Pull that in here, grab a quick picture. Unmute and ask if you got it now. Any questions? Darn it. That was not really what I wanted to do, but that's okay. I'll fix it in a second. Get that put there and pull it back up. Any questions before we advance? All I got to do is unmute to ask. Anybody? Okay. Now, when we were doing the Delta Math yesterday, we came across these problems of continuous interest. And unfortunately, I didn't notice when I spot checked the topic that they had continuous interest mixed in with the other compound interest formula problems, which is part of the reason why we're extending this assignment and making some adjustments to it. Okay, is because those problems were coming up and people are like, well, what do I do with that? I don't know how to put in continuous. What does that mean for n? So this requires us to introduce the number e, which you probably have seen in Algebra 2. E is known as Euler's constant. It is also known as the natural base. This is because E comes up all the time in real world problems. Things like population and growth on trees and things like that. We see this E value come up in nature all the time. Now, E is like pi. It is an irrational number that goes on forever and never repeats. It is approximately, and this is the value that we will use in class, 2.71. Now, E is actually equivalent to the limit as x approaches infinity of 1 plus 1 over x to the xth power. But you can't just plug infinity into that because 1 divided by infinity is essentially 0. And raising something to the infinity power is essentially impossible. Okay? So the bigger the value that you plug into that expression for x, the closer you get to the actual value of E. Now, that being said, human tools don't need to be all that accurate. It's the same thing as pi. You don't need to know pi to 200 digits to get an accurate measurement. So in this class, we will be using the approximation E is about 2.71. However, it's worth noting that your calculator has E built in. If you look at the left side of your calculator, the left column right next to number 4, you'll see a button that says LN on it. And directly above LN in blue, it says e to the x power. So the natural base is available to you on your calculator, and much like pi, you should be using your E button. Okay? Lovely. So let me grab a quick shot of this stuff here, and we will go on to talk about continuous interest.
Can't we also use the E that's on the division button?
I think so.
Okay, because I've been doing that and it works just as well.
Yes, if you need it, I basically use that if you need just E, and you use e to the x if you need e to a power.
Got it.
Yep. Okay. Let's put that in there. And back here we go. Come on. Come on. There we go. All right. So let's talk continuous interest. Essentially, continuous interest is where the... Uh-oh. What did I screw up? No. Come back. There we go. Is where we are continually, we're compounding an infinite number of times per year. So when we see that word continuous, that is compounded infinitely many times per year. That is the word that we say for, I have no idea if I spelled that right, continuous. I guess I could just look right there. Hey, I spelled it right. Cool. It's an entirely different equation, essentially. Okay, because we can't plug in infinity in for n. Okay, we can't take n equals infinity and plug it into this form to our compound interest formula. So we actually have a separate formula for when we see this word continuously. We use this formula right here instead. A equals P times E to the RT power. P equals E to the RT tau power. So we're going to look at an example of this after I grab a quick screenshot again to throw into the notes. Any questions on this before we advance to the example stage? We're almost done for the day. Any questions? Okay. Again, if I'm going too fast, I'm happy to put any of this up again later if we need to see it again. Let's look at example 3. You invest $10,000 into an account compounded continuously at an interest rate of 9%. How much money will you have after 40 years? So again, we just need to go in here and identify these different values for what they are. We are investing $10,000, so that's P. Okay, as soon as we see this word continuously, that tells us we're going to use this equation. Interest rate of 9%. R would be 0.09, because remember, we need to turn our interest rate from percentage into decimal. And that should be, other than T, which is 40 years, everything that we need to solve this problem. Okay, so we're using the equation A equals P, which is 10,000, times E to the 0.09 times 40th power. Okay, and we're going to feed that to our calculator. So we type in the 10,000, and then we would hit second ln, which inserts E and puts us up in the powers. Type in 0.09 times 40 for the exponent. So the keystrokes would be 10,000. So we'd enter that number, 10,000. Then we would hit second ln, and then type in 0.09 times 40. That would be our keystrokes there. Okay? 0.09 times 40. And we get $365,982.34. Again, that is rounded off to the nearest cent, but that is how much money would be in that account after 40 years. Darn it. Okay, again, to get that we're going to type in the 10,000, then hit second LN, which is right next to 4, and type in 0.09 times 40 for the exponent. Any questions before we do example 4, which I believe is the last example in our notes for today? Okay, anybody need more time here before we advance? You can just raise your hand in the chat. You can just say something, anything. Anybody need more time before we advance? I'm probably getting cold and in trouble because I haven't resent the problem solved. Okay, here we go. So finally, it says you want to invest $5,000 for 20 years. Which would be the better investment? Option 1, 8.25% interest compounded continuously, or option 2, 8.6% interest compounded semi-annually. So we're going to split our work area in half here, and we'll do option 1 on the left, option 2 on the right. In both cases, the principal is 5,000. The time is 20. For option 1, our interest rate would be 0.0825, and we're compounding continuously, so we would use our continuous equation. A equals P times e to the RT power. For option 2, we still have the principal of 5,000. We still have the time being 20. We have an 8.6% interest rate, which would be 0.86. And we have compounded semi-annually, that word meaning n equals 2. We would be using our normal compound interest rate equation here, which is A equals P times 1 plus R over N to the NT power. So from there, all we need to do is plug in and see which one results in more money. So for the continuous, we would have 5,000 times E to the 0.0825 times 20th power. Again, we feed that to the calculator. We type in 5,000, hit second LN to get the e to the power. Type in that decimal times 20. That would result in a balance of $26,034 and approximately, rounded off to the nearest cent, 90 cents. For option 2, we would plug in our values. That would be 5,000 times 1 plus 0.086 divided by 2 to the 2 times 20 power. And again, we're just going to feed that to our calculator, being very careful that we type it in exactly correctly. So 5,000, open parentheses, 1 plus 0.086 divided by 2 to the 2 times 20th power. We are using two different formulas because one of them is compounded continuously, which requires the special continuous equation. whereas compounded semi-annually is normal compound interest formula. So we have this special situation here. Whenever we see this word, that means we have to use the special formula. Okay, anytime we see any other word for how many times a year it's compounded, we use the normal compound interest formula. So that would result in $26,936.57. So essentially, it's worth noting that the interest rate itself is not as important as how often you are compounding. Okay, it's not as important as how often you are compounding. Okay, you can have a lower interest rate and compound more times per year, and you'll end up with more money down the road. Now, I know that didn't happen here, but I mean, that interest rate for the continuous is significantly lower than the 8.6% for only 2 times per year. And it almost makes up the difference that quickly. Like we're talking, if we went to 21 years, I'm willing to bet that the continuous would have more money in it. Okay. So when you're, I mean, this is real life stuff here. When you're putting money in a savings account, you want to know 2 things. What is the interest rate and how often is it compounded? Okay, because you can use this exact formula as what they use in the real world to figure out how much money should be in your account. This is what the banks do. Okay, so that is, I believe, the end of the notes. Correct me if I'm wrong. There aren't any more past that, are there? I think that's it.